Just want to make sure, so all of you are seeing a slide, right? So because I'm using dual monitor, so I just want to make sure you see the slide, not anything else. Right.
Yes, sir.
Okay,
Yes.
thank you. Yeah. Let me take it closer. Okay, let's begin. I think students are still on their way, but we are recording, so it's already 5:02. Okay, last time we see the maximum likelihood estimation. Basically what we do, I think let's recap a little bit. Okay, so initially we talked about there are two methods for estimating a parameter, okay? The first is called a maximum likelihood estimation, right? The second is called the Bayesian estimation, right? So the difference is that for maximum likelihood estimation, you just look at the, you don't look at the prior, you just look at the numerical probability, okay? Well, for Bayesian estimation, you also need to look at the prior, and the prior is usually a distribution. Let's say how much you believe that one class is more like in the majority, the other is the minority, right? So in your background database, okay? So this is called a prior. If you don't have any prior information, you will probably just use maximum likelihood estimation, okay? And in that case, we will find the most likely theta to generate your data X, okay? And so, yeah, let's continue. And for classification specifically, we are using, later we will talk about regression. Okay? For classification specifically, we are using Bayes' rule, okay? That we talked about earlier, right? So in Bayes' rule, we say that if you're given a data X with a few attributes, so this is a feature vector, okay? And you want to decide whether this data belongs to class 1 or class 2 or class 3, which I it belongs to, right? So C is a class, okay? In order to do that, you know that you can compute it like, let me see whether I can use this. Oh, I need to open. Yeah. Okay, so let me see. So change the mode. So we know that, for example, this term, maybe I should make it, okay? Yeah, this term here, okay? This term itself is what? Itself is px, okay? Right, so, and the x itself is actually, a constant, right? So, yeah, let's plot it in a better way. Okay? So this term, down here itself is actually p x. And so this is because if you look at this term, right? So this is basically joint probability of x and ck, right, belong to ck. And for k terms, basically down there, it's x joined with each class, right? So summing them up is giving you px, okay? So this is the Venn diagram we talked about, right? So if you have 4 classes, okay, and this is your x, right? So this is x. And joint probability for C1 maybe this one, okay, the first class, because this corner is C, okay? For C2, maybe this code. Okay, add all them up, give you px, right? And this px usually we will not consider it because this px is a constant. Okay, we usually treat it like a constant. And so all we look at is what is up here. Okay, these two. Yeah, I'm not used to the tool. Okay, so yeah, so basically this is the constant for any for any class. Okay, for any class, this term is the same. Okay, for any I. So when you compare C1, C2, C3, the term here is the same. We are mainly compare with the other terms. Okay, right. So this is the prior. Okay, this is what we call prior, and this is the generative probability. Right. So if you truly belong to C1, right? So what's the probability to generate? Right. So generative probability. Okay, and this term itself is called posterior. Okay, this is posterior. Okay, so this is prior before you see X, right? You don't see anything. How much you'd likely believe that the class belongs to C1, right? And then after you see X, how likely you believe that this data actually belongs to C1, right? If you don't see any attribute of it, you have a prior belief. Okay. So this is only used when we consider, consider classifications. This is called a density estimation. Right? If you belong to a particular class, how likely you will generate different features. Right? So this is called the generative class. Okay, it's a generative probability. So this is a generative model. Okay, and then combined with the prior, you will get the posterior, which will be used for classification. Right? So if you see X, how likely it belongs to C1, C2, C3, right? You get the assigned to the most likely. Okay, so basically we need these two terms, right? So, which is put here. Okay. Right, so this is basically the first method for parametric estimation, which is called a maximum likelihood. Okay, and it finds theta that makes, you see the observed data, right? So we assume the data is sampled, by the way. Okay, you see from a underlying distribution, let's say C1's Gaussian distribution. Yeah. Okay, so makes this sampling probability most likely. Okay, right? So if your distribution really have this theta parameter, how likely would generate X? Right? We want to find the theta that most makes the occurrence of this data set most likely. Okay, so this is an right. And so as a recap, usually we will not consider, because this is independent data sets, right? Yeah, and data sets, right? So because they're independent, we can use a product. Okay, but we usually don't want to work with product because when you take a derivative, it's super complicated, right? So last time we talked about we will actually use a log, right? So after taking log, this is called a log likelihood, right? And the product becomes summation. Of course, each term you need to take log, okay? And then based on this, we can take derivative theta, for example. And because of summation, right? Basically each term you take the derivative theta and you sum them up, okay? And so this is more tractable, okay? And so maximum likelihood estimation, just say, hey, give a particular theta, right? Because this data is what you see, it's a constant, right? So this summation is a given theta, you will have a summation value, which is the likelihood, okay? Right, so we want to find a particular theta that maximizes this likelihood, maximize the likelihood that you see the data X, okay? Right, so we write it like this. We want to find a particular theta. So when we put in this function, which is basically here, we will see this X with most likely. This L value is the most likely. Okay, we want to find this theta. Usually we use theta hat, which means the estimated value of theta, to denote the estimation. Okay? It's not maybe the underlying theta is not this theta. Okay, this is our best estimation. Okay, and we also call this usually.
Professor.
Yeah.
Yeah, I have a quick question here.
Okay.
If for the given data X, what is the probability of theta being high? What we want is highest probability theta, right? If you see the first equation for a given data, log of why we are again considering given theta, what is the probability of, x, and before that, why are we considering given x, what is the probability of theta being in that distribution? Likelihood.
Yeah, I don't quite get what you want to say, but this theta is this theta is a model, right? So we assume a distribution, right? This is a parameter of a distribution, I say Gaussian theta, okay? And this is our assumption, inductive bias, okay? As we assume the data really generate from the Gaussian distribution, for example, then how likely will see theta, Cx? This is our assumption, okay? The truth may not be exactly Gaussian, right? So it may be some more complicated distribution, but if we assume Gaussian, then we will get this likelihood, okay?
Okay, Prof.
Yeah, this is our assumption, right? Does this answer your question?
Similar, but anyways, it's fine, Professor. I got it.
Yeah, this is our assumption.
Man.
We have to assume whether rectangle or some curve, right? If you remember the previous example, or we assume linear, or quadratic, or ordinary polynomial, even though it's a sine curve, right? So the ground truth may not be Gaussian, but we want to approximate. We assume the model is Gaussian. Okay.
Okay, Professor.
Yeah. So if P is really a distribution, right? So it may not be Gaussian. Okay? It could be exponential distribution, right? So different distribution all have a parameter theta. Okay. And then we want to find the particular theta that maximize your likelihood x, right? Because you give a particular value of theta for this distribution, given the distribution for a particular observed attributes, the probability. Right? If you give a particular theta, you sum all the data items probability, right? And you will get a value likely. Okay, you want to maximize your likelihood. Right? You give, let's say, theta different values. Right? You find the particular theta that gives you the maximum L. Okay, that theta is what you want to find. Right? And we assume the ground truth theta is really like this. Okay. So this definition actually has some problem. Okay, so for example, if you consider, let me see, maybe I should use annotation. So it's always like you can. Okay. So for example, if you consider your space is theta, okay, right, and the y coordinate. Okay, so I think not used to this plot. Okay, so for example, if you consider, let me just do this. Okay. If you consider, let's say, this is theta, okay, and this is L, right? So we are saying that, let's say, we are finding this particular theta, right? Your L value is the biggest, okay? Right. But if you look at the theta nearby, right, this value is also almost equally likely, right? Not so small, right? So, but we assume the theta is actually this theta, okay? We do not even consider the possibility that theta is the next value, okay? Right. So this is because this is maximum likelihood estimation, okay? And this may not always work fine. Okay, this is our best effort solution, right? So maybe the true theta is a little bit here. Okay, it's unlikely to be here though. Right? So this is our best guess. Okay, so Bayes estimation basically overcomes this issue, right? So we consider this theta, we also consider this theta, we also consider this theta, just to adjust their probability, right? And aggregate the possibility. But that is more expensive. We'll see that later. Okay. And the last time we talked about, we will see univariate data, which means we only look at something like something like y is equal to f theta x. Okay, right. So this x is not a scalar, right? So if we look at the multivariate data, right, we are looking at y equal to f theta. Okay, x, but this x is a vector. Okay, it's not just one dimension. It's multivariate. Okay, and so again, theta itself is almost always a vector. Okay, yeah, right. At least it's not just a one vector, not scalar. Right. So that's why even if the X itself is univariate, okay, our derivation still will consider high dimension space, because when we take derivative, we take derivative theta. Right? We want to find theta, X are constant. Okay, right. So it's just that univariate functions are easier. The forms are easier. Okay, multivariate is more complicated if you think about Gaussian distribution, right? So it doesn't mean that our parameter is univariate. It's just the X is univariate, so that F is simple to interpret. Okay. And here, if we say that Y is a probability, right? So F is the distribution. This is called the generative model. Right? So we are doing density estimation, density of this distribution, right? Because it's a PDF. Okay, we talked about what is PDF last time. Right? D means density. Right? Well, if Y is class, right? 1, 2, 3, C1, C2, C3. Okay, C1, C2. Then it's classification. Okay. And here our classification actually uses density estimation, right? So if you look at our derivation before, so this is density estimation. Okay, this is classification, right? So when you see X, how likely to have CI, right? This is density estimation. If we assume CI corresponds to that distribution, how likely to have X? Okay, and if Y is the a value, then like a temperature or something else, a continuous value, then it's a regression. Okay. And last time we have seen the Bernoulli distribution, right? So basically, the Bernoulli distribution is a discrete random variable with two possible values, 0 or 1. Right? It's like a Bernoulli trial. Okay. Bernoulli trial is basically saying that, so 1 is succeed. Okay. And 0 is fail. Okay, so if you trial, how likely will succeed, right? So there's a succeed probability P1, right? So x equal to 1 means you succeed, right? And x equal to 0 means you fail, right? So it's failure probability P2, right? So P1 plus P2 is 1, right? So basically P2 is equal to 1 minus P. And so of course you can use this as P and this as Q, have two parameters, right? So but their sum is 1, right? So it makes no sense to have two parameters and then add a constraint that P plus Q equal to 1, right? In this kind of cases, we usually, for binary cases, we usually eliminate half of the parameters. Okay, we only consider one parameter. Okay. So here is the mass function that we see before. Okay, P0 is a succeed probability, basically this guy. Okay, and 1 minus P0 is a failure probability, basically this guy. Okay, and we have explained why this is like this. But if you give 0 and 1, you will see that the probability that x equal to 1 is really P0. Okay, if you compute this. If you give x equal to 0, you will see this is really 1 minus P0. Okay, because we have seen this again, so I will skip this. Okay, and now one thing you need to pay attention is that this thing is saying that for a particular x, right? If you try 10 times, right? This is just one of them, one time. Okay. Usually in our training data, we will see maybe 10 trials or many trials, right? So there's a superscript L with parentheses. Okay. So in machine learning, we usually add parentheses. If not parentheses, this is equal to like x times x times x L times, right? So this is not what we mean. Okay. This is the L's data item here. So we add a parentheses. Okay. So this is where we have the joint probability. Okay. Joint probability. Okay. And so let's just look at one of them, right? So, and let's go back to our previous derivation. Okay, so let me see. Yeah, previously we said that if you have one data item, okay? If you have one data item, then if you see 10 of them, right, it's a product, right? Because each trial is independent from Bernoulli, okay? And then we take a log. This thing becomes summation and the log goes inside. That gives our next page, right? So in the next page, basically we have this, right? So keep in mind that we have, so from now on, we will not emphasize this again. Let me see why this is not working. So we will assume you already know, get familiar with summation, and the log. Okay, so if you have 10 data items, right, a summation of 10 of them, but each is a probability, but take log. Okay, so this is what we will assume. Now we know that this is just one item, right? So if we consider summation and take log, right? So we will get the next page. Right? So summation, just to take log. Okay, this is take log of this term. Okay, so we know that. So how to derive this, right? So let's take a look at. Okay? So basically, this is A, this is B. Then if you think about take log of this thing, it's equal to log A plus log B. Right? So this is equal to log P0 x plus, this should be log, okay? 1 minus P0, 1 minus x, okay? And importantly, we have another formula. I'm not sure whether you are familiar with log. So basically log A B to the power of x is equal to what? Who can answer me?
Log x to the base x to the power b to the power a.
Okay. Can you repeat again?
So log base x b to the power a. Is that what you're looking for? Changing the
Yes,
base.
this A is a base, right? So if you can ignore A if you want. Okay, like here we have a natural.
X log B.
Log b. Okay.
Yeah, x log B. Okay, right. So the x to the power can be moved to before. Okay, so this is basically when you study log maybe in high school, you should know this, right? So basically we say this x can go before. Okay, and similarly this 1 minus x, right? So can also go before. Okay. So this gives us the next page, right? So after going before, no, we have this, right? So this is just one term for L, okay? We need to sum all of them, okay? And then we will be able to show that, this is just a likelihood formula, right? So these L are the samples, okay, from a one-dimensional linear trial, right? 0, 1, 0, 1, 1, 1, 0, right? So this is, let's say, what you see, okay? And it's for each P0 and for those 0, 1 sequence, right? So you will get a 1 likelihood, right? So we want to try all P0s and then find the most likely, right? Because there are infinite number, right? Uncountable number, right? P0 can go from 0 to 1, right? So we cannot just try all of them, right? So what we need to do is using optimization, right? And after doing optimization, you will see that this is really the result, okay? So P0 is actually equal to what? Equal to sample mean, because this is sample. Let's say, I think I need to draw. No, so let's say this. Let's say you have 5 values: right? 0, 1, 1, 0, 1. Right? So you succeed for 3 times. Okay. So what we will do is, this n is 5 because we all together try 5 times. This is their summation. Okay. So 60% success probability. Right? Because it's 5 divided by 3. Okay. N is 5. The summation is 3. Right? So this is really simple. Right? This makes sense, right? If you try 5 times and the 3 times you succeed, right? And each time is a Bernoulli trial, right? So with fixed probability, then that probability is most likely 60%. Okay, right? Because if you try 10 times, it's likely 6 times you succeed. Any question? So this called an estimate. Estimate means the value, okay, the hat. Okay, maximum likelihood estimate. You can also call it estimator because of both of them. Okay. And the question is why? Why if we give this P0 here, right? L is maximized, right? So if we give another P0, actually the value is not going to be as big as this one, right? So this is the question. So this is sampling. Okay. Yeah, let's, I think we need to stop share and switch to, okay. Yeah, so can you guys see here?
Yes, Professor.
Okay, sure. So basically, here I need to use a zoom center with my mouse. Let me see. So here, basically, if you let me just switch. Okay, so if you look at, this is what we get previously. Right? So this is success probability, right? So this is failure probability, basically. Okay, and if you take the joint probability, and finally we get this. Okay, this is what we get, the log likelihood. Okay, notation is a little bit different, but you can see the shape on it. Right. Now let's think about what we want to maximize. Right? We want to maximize this, find a p, maximize this, and it will also maximize this, right? Because they are just different by log. Okay, so the log by default we are talking about log e. Okay, log e of something in this shape. Right? So if you're, let's say, if you prefer to take log, let's say this value, these two values are smaller. Right? So after taking log, these values, log value is still smaller than this value. Okay, so they keep, because it's monotonically increasing. Right? So if you maximize this calligraphy, you also maximize this. Okay. Okay, so now, because this is easier to see, okay, let's just look at this equation, right? So, and we know that P is what? P is a probability, right? So it can only go from 0 to 1. Right? It cannot go below 0 or larger than 1, okay? And now let's think about the two extremes, right? So if the value is 0 or the value is 1, what will be the result? Let's first look at if this P here is 0, what will be the result? Who can answer me? Yeah,
Can you repeat the question?
Can you repeat the question?
Yeah, right. So this P is 0, P to the power X is 0, right? And this is a product where one term is 0. Okay, it will be 0. Is okay? I assume
It's
okay.
just one.
What? Deepak?
P.
Yeah.
0.
Yeah, I understand this term is 1, right? But this term is 0, right? If 0 times anything is 0, it's okay?
It's 0. It's 0.
Yeah, because this term is 0, right? If P is 0, this term is 0. Then take product.
Oh, yeah, right.
Yeah. Okay. Yeah. Now, if you look at 1, it's the same, right? So if P is 1, this term is 0, right? And then you take product of something. One term is 0, the first term is 0. Okay. And you know that, what is this? Can you guys hear me? Because I see an internet unstable note. Okay, yeah, if you cannot hear clearly, just let me know. Right, so, if this L, okay, this L is what? This is likelihood or probability, right? So this thing should also be within the range 0 to 1, okay? And we know that, so this L can be at most 1, okay, 0 to 1, okay? And we know that if you look at this P, right, on the one end 0 and the other end both are 0, okay? L equal to 0, right? So we will find the maximum in somewhere middle, okay? It cannot go below 0, right? Okay, so we want to find a P in the middle that maximizes the likelihood, right? And so there are several questions, right? First, whether this function is concave. If it's concave, then we are done, right? So we take a derivative equal to 0, right? And this is really maximum, okay? Well, the question is whether this function is concave, okay? Actually, we don't have to prove this function is concave, right? If we can show that there's only one extreme point, which means if we take a derivative of partial L and partial P, right? And within the range of P 0 to 1, there's only one particular P where the derivative will be equal to 0. Then we are done, right? Because even if you have some value, something like this, okay, this is P, let's say this is L, okay, you have something like this, okay. That's also fine, right? So this is not concave, right? This is above, and if you look at these 2 points, this is below, right? But this is still maximum, right? So if you have it's more like a Gaussian shape, okay? For example, if you think about something, okay? So from 0, it's like a Gaussian shape, right? So if you look at these 2 points, right, the line is above, okay? And if you look at these 2 points, the line is below, right? So it's neither concave nor convex. But if you take derivative 0, this is still the maximum value, okay? But So the reason is, if you want to take a maximum, it must switch from increasing to decreasing. Right? So the derivative will be 0. Of course, the function had to be smooth, right? So like the previous one, it's a little bit complicated. Okay, so it's not really the case. So if you cannot take a derivative, okay, if it's smooth, and then the maximum value must be up and down, right? So then here it's flat, okay, derivative 0, and it's just only one value like this, right? So of course, both sides is smallest value, and there's only one value that will reach maximum, even if it's not concave. This is still the value. Okay, so we will see this later in Gaussian distribution, but here we actually can prove that this thing is concave. Okay, so then the problem solved. Right, so basically, if it's concave, we know that the value goes to max and then decrease when you go from 0. Okay, now let's take a look at how to compute it. Right, so now let's go back to this function. I think I need to show. Now let's look at this one. Okay, this is what we derived last time. Right? So, and now the first thing we want to do is, because we want to prove concave, we want to take second derivative, right? But before taking second derivative, what we need to do is we first take the first derivative, right? Then we take p again, we will get this, right? And we need to take the first derivative and it's up to 0 anyway, right? So the first thing we do is always take first derivative, okay? Now let's look at what will be the result. Now, if we take the first derivative, remember these x are 0 or 1, the constant, right? 0, 1 values you see, okay? So this is a constant. If we take derivative p, this is constant. Right? So basically, we are taking derivative log p. And we know that if you take a derivative log x, it's 1 by x. Right? So that's why this is 1 by p. Okay? Now, this is again a constant. Okay? So the constant is always p. Right? It's just a coefficient. Now we're taking derivative this term. Right? So this is using chain rule. If we assume u is equal to 1 minus p. Right? So using chain rule, we will first take this log u, right? So log u by u, okay? Then we will time, log u to log p, right? So if you look at the first term, right, log this term is 1, log u, take the partial derivative u is 1 by u, okay? So that's u, right? So this is why it's 1 by u, right? Then we look at the second part, okay? U by p, u is what? U is 1 minus p, right? It's coefficient negative, okay? So that's why we have the negation, right? Any questions? Yeah, assume this is fine, okay? Now, because we want to find the derivative equal to 0, right? So we just set this value to 0, okay? Now, all we need to do is solve this equation, right? So how to do that? So this is very simple, actually, right? So if you just think about, if this is equal to 0, basically this thing equal to this, right? So, and this equal to, if you time 1 minus p to this and p times this, right? They are equal, okay? Right, so if you look at on the left-hand side, this thing is what? It's a 1 minus p and summation, okay? I equal to 0, 1 to n, and so on, okay? And if now we can just see that this term is this term, right? So no, because this 1 times the summation is just a summation, okay? This is p times the summation, right? So this is this thing times this thing, right? It should be equal to this thing times this thing, right? So what will be the result here? Right, so that's clear, okay? So if we time p times this summation, right? So this basically is this, right? So now we just need to solve this equation and find the p, okay? Let's look at the right-hand side here. Okay, the right-hand side is equal to what? Equal to p times this summation of 1 is actually n itself, okay? Because, some n such ones, right? It's n, okay? Minus, then this has to equal to I. So this is really summation of I equal to 1 to n, and so on, okay? Or we can write it like this. This is Pn minus P times the summation, okay? And you see this minus P times summation, minus P times summation cancels, Right, so basically we have this term, go to this term. Right, so now our p, if you want to find p, you just divide the n. Right, so divide the n, this n missing, then this is the result, and which is this. And this is what? This is what we call the sample mean. Right, so this is what we see in the slide. Okay. Any questions? So we can see that P is really if you think about the P to L curve, it's something like this, right? P is really the only point where the derivative is 0. Okay, it's gonna be the maximum, right? So if it's only one, then it's gonna be the maximum. But it's not the only one; there's no guarantee, right? So you think about it. You have this, this, and this, right? So you have 3 zeros, right? So then you don't know which one, right? So you need to find the maximum among them, okay, right? But here it's only one, so it must be the maximum, okay? And so right now, so actually it's already done, but if you want to show that this is concave, right? So this is also not difficult, okay? So because, let me see. Because we already have this, right? So derivative of P is this thing, okay? Now if we want to compute the second derivative, right? So we just take a derivative of this P again, okay? Take this thing to derivative P again, okay? So this is what we are doing here, right? So again, you know, so because this thing is constant, right? So we are taking derivative this P, okay? This P is 1. This is to the power minus 1, right? We know that P to the power 1 is, if we move the minus 1 before, then P minus 1 minus 1. Right? So this is really equal to minus P squared, okay? Right, so this is why we have the minus P squared here, right? So if you look at the second term, so it's kind of similar, right? So, you know, this is the minus P squared, right? So, but we have the chain rule, right? So because we will treat this as U, right? So we have a negation here. But the negation and this negative, if in the first chain rule, type derivative to U cancels, okay? So, you know, this minus 1 and when we take a partial derivative 1 minus P, we will also have the negation, they cancel. So y, this is why this minus is U capital, okay? Now let's take a look at why it's concave, right? If you want to show it's concave, then you want to show it's always negative, at least in this range, P equal to 0 to 1, right? Is this really the case? It's not difficult to see that. So because, you know, this term is positive, okay? Because P squared is always going to be non-negative, right? So, and this summation of 0 and 1s, right? It cannot go negative. So this term is non-negative, okay? And similarly, this term cannot be negative. 1 minus xi is still 0, 1, right? So, and this is non-negative. So you can see this term, these are two positive values, but they all have the negation sign, okay? That's why.
I have a question.
Yeah.
This xi is a Bernoulli distribution?
Xi is a Bernoulli distribution, right? We talked about we have 5 troughs, 0, 1, 1, 0, 1.
Oh.
Okay? So this is x1, this is x2, okay? So actually this xi is in our notation.
But for a,
yeah. This is what we see, right? We see these 5
because
values.
for every cases it might not be positive, right? Only for this Bernoulli we got a positive.
Yeah, we're just talking about Bernoulli distribution, right? The Bernoulli distribution x is 1 minus x is also 0, 1. It's just a negate. This is 1, 0, 0, 1. It's okay?
Hey, could you show more examples in the future? Because most of the time you're showing just math.
Hey, can you speak a bit louder? I cannot hear clearly. Thank you.
Yeah, can you hear me?
Yeah, now it's okay. Yeah.
Can you hear me? Okay. I was just asking if you could show more examples in the future, like code examples or diagrams, like where this is running. Because most of the time you've been talking about, well, you've just been showing us math theory. I'd like to see more examples. It would help me learn better.
Yeah, but we are talking about parameter estimation. So what we will do is basically using these parameters. But if you look at scikit-learn, right? So you are doing scikit-learn, okay? Scikit-learn basically is a fit function doing this, right? So you put the x, which is 0, 0, 0, 1, 1, 0, 1, right? And it will tell you, hey, this theta should be what? Theta should be 60%, okay? And then later when you predict, it will give the but here, because we are teaching these parameter estimation, then it's really a little bit abstract. Right? So we are trying to balance theory and practice. Okay, most of the projects will be practical, and you can also ask me practical questions. I will also point to practical things like libraries, but because this thing itself is optimization, right? So there's not much other things we can do. Okay. Yeah, again, machine learning is kind of like this. Okay, if you look at, I think one example that I can show you is, so we are trying to keep a low profile, not to do too much mathematics. Okay, but this is really, so there are two things, right? So one is, let me share this. Yeah, so so there are two cross lines. One line is, for example, math, right? So, and one is coding, okay, projects, okay, right? And most people like here, okay, right? But some people like here. There's some very small amount of people, okay. But if you stay here, you're only understanding things shallowly, and you cannot dig deep into the model and change it according to the data requirement, okay. So that's why we let you go here a little bit, right? So, and then you can come back and change the model a little bit, and change the library. Otherwise, all you can do is call fit, right, and predict, okay, and using existing models in secular, right? So we want to also teach you a little bit of techniques that you can do, let's say, research, not just using the machine learning model, okay? Because using machine learning is easy, okay? One example that people can get crazy. Let me see. For example, we can take a look at a particular paper. So people are really doing this, right? So like this is social media analysis. And if you look at the paper, it's not so interesting. Okay, so if you look at the paper here. So they are just saying how to optimize updating. They formulate the social network problem, let's say equal to a graph analytics problem, because it's friends, tweets, so forth, right? So then all what they come about is define notations and and then define optimization problems, and they solve it. Okay, so there's not much interesting thing here. It's just that if you know these maths and formula, right? So I understand, but if we talk about only something here, okay, if we talk only stop here, then you can call scikit-learn's library or some existing library model and put the X, they will fit the parameters and then can transfer it. Right? So, but we will go a little bit deeper. Okay, yeah. So this is what we are trying to do. Let me see. So I see a chat. Okay, so okay, now let's move on to the next example. All right, so yeah, the next example is, previously we say that it's each trial, each time you can only have 0 or 1. Okay, only 2 possible values, right? So, but that's not enough. Okay, right? So sometimes each time you have, let's say, 3 values. You can take 0 or 1 or 2, right? So this is called a multinomial distribution, right? So you can have up to k possible values. Okay, it's like k classes. So you have a lot of draws each time you have a value. Okay, for example, you have 3 colors, ball colors, right? So red, blue, and gray. Right? So each time you take a ball, it will have some particular color, right? So, and yeah, let me see some more chat.
Sorry for interrupting, sir, but I think you are in the. I can see.
Oh yeah, I see. So let me switch. Okay, so because I'm using dual screen. Thanks for the reminder. Can you see it now? The full screen?
Yes, sir. Thank you.
Okay. Yeah. Let me see what's the other chat. Okay, so yeah, so now it's kind of like, each time it's not just 0, 1, right? You can have more than 2 values, right? And in this case, it's a generalization of Bernoulli distribution. Right? So now it's actually, instead of saying we have the 0, 1, 2, right? So what we will do is we will use so-called indicator variables. Okay. So what the indicator variable doing here is saying that, just a minute. Yeah, for example, now each time you try, right? So you can have you are picking from 1 to 3, oh 0, 1, 2. The next time you will also have choice 0, 1, 2. 0, 1, 2. Okay, this k equal to 3. Okay, maybe the first time you draw a 1, the second time draw a 0, the third time you draw a 2. Okay, but by multinomial distribution, we are saying that the probability of getting p0, right, getting 0, and probability getting p1, and the probability getting p2. Okay, they are fixed for different tries. Right. Okay, each time you try, there are all these 3 values. Okay, and the sum is again still equal to 1. So if this is 20%, this 30%, this should be 50%. Okay, right. And instead of saying something like this, we actually, for each data item, we actually give a so-called one-hot encoding. Okay, this is called a one-hot encoding. Right? So yeah, I'm not sure whether the handwriting is a little crazy. Okay, so let's say for this term, actually, you have an indicator variable. Right? So by the way, this is for the else data item. Okay, we will ignore this for a particular data item. Okay, then we will have, because k equal to 3, right? So we say k equal to 3. Then we'll have x1, x2, x3. These x are indicator variables. Don't mix with the input. Okay. Actually, if you want to say, hey, this is the else data item, you can do something like this. Okay. Right. So this is called one-hot encoding because, for example, if your class is 1, okay, then what you will have is 0, 1, 0. Okay. Right. So if your class is 2, then this term will be 0, 0, 1. Okay. This is called indicator variables. If you look at particular xi, let's say x2, xi, it's just determining whether your state is 2 or not. Right? So for example, if this state is 2, then your x2 is 1. Okay. Well, for this term, right, your value is 1, so your state is not 2. So that's why your x2 is 0. Right? Any questions? Okay, let's continue. Yeah, I think maybe we can go a little bit more than here. Let me try to switch between the screens. Okay. Yeah, desktop 1. So the one-hot encoding is actually everywhere. If you look at, because machine learning works with one-hot encoding a lot. Okay, encoding. For example, I'm not sure. Maybe in scikit-learn it already has a function, right? So this is called one-hot encoding. Okay, and what it basically do is if you give this kind of let me see. If you say, hey, I have 2 classes. One is, so this is 0, 1, 2, 3. So yeah, well, if you give it, let me see how this is. I think this is column-wise, right? Because the summation should be. Okay, so basically, maybe you have a binary classification, right? Male or female, right? So one-hot encoding is saying something like, right? So this is the 1 vector, right? X1, X2. Right? So this is 1 vector. This means this guy is maybe 1 is male, this 0 is female. Okay. So if this is the case, then we have 4 data items, right? Each is binary, something, right? Okay. Yeah, so there's a position key in terms of column. So then you can go into your machine learning model. For example, if you look at gross entropy loss, right? So this is actually what we just see before. Okay, what we are seeing now, okay, for gross entropy loss. Right? So this is exactly what we are seeing. Okay, this is exactly what we are seeing for binary class. Okay, in general, for more complex class, what you have is something like this. Okay, so basically, your ground truth class should be something like this. But if you have class 1, you should encode it as 1, 0, 0. Right, and then compare with something on the left-hand side we will talk about later lecture. Okay, Right? So this one-hot encoding is often the first time you transform your Y. Right? So the Y is your actual label into a one-hot encoding. This is quite common in machine learning. For example, so if you look at yeah, so this is how I kind of help you connect to real stuff. Then later, when you really use them, you kind of know how they correlate to this. Right? So you can see one hot. In TensorFlow, there's also one TFL. Right? So, and if you look at, I think even for NLTK, right? So they have one hot encoding. NLTK is a library for one hot encoding work back and back. Okay, so this is for yeah, so basically it's everywhere, right? So this is the concept. Yeah, let's share screen to. Okay, I hope you kind of get an idea of what we are talking about here. So at least the definition. Okay. So again, there's a constraint, right? So if you look at here. Okay. Previously, we say that you can take 3 values, 0, 1, 2, right? And maybe, so this will be 20%, okay? This may be 30%. This may be 50%, right? Their probability sum up should be equal to 1, okay? P0, P1, P2 equal to 100%. Okay, this is 100. Right? So this is the one constraint. And when talking about constraint, we know that we have the constraint optimization. Right? This is where Lagrangian comes in, okay? The previous example is a special case of this example. If you look at the previous example. So let's go to the previous example. Right, so if you look at the previous example here, you can equally say this 1 minus P0 is P1, okay? Basically, they're equal, okay? But with 1 minus P0, we don't need another parameter, P1, okay? Because if they sum up to 1, we don't need to constrain them. But now we have more than one class, so we have a constraint. Right? So if you look at the problem mass function, okay? If you look at the problem mass function, it's kind of similar. Right? Okay, if you look at problem mass function, yeah, again, so I want to emphasize. So I understand the mathematics may be crazy for some students, but that's where you get promoted, right? In some way, right? In your techniques. Right? So if you keep telling you just scikit-learn and call simple models, and people already code for you, just put input and copy it, right? You never improve. Right? So this is painful, right? If you go up and go deeper, it's always painful, right? But that's the purpose of this course. Okay, you can try to catch up a little bit. Even if you don't get everything, you can still pass the course easily. Okay, so because we will not only the 2 written assignments will be a little bit difficult. Okay, the programming assignments are not so difficult. Right? So yeah. All right. So if you look at this definition, right? So why this is the case? Okay, you can see this is if you consider P0, P1 in the previous example, it's exactly a generalization of that. Right? So so if you look at here, we know that if we have a one-hot encoding, something like this, right? 0, 0, 1, which means you belong to class 2. Okay, so what you will have is something here will become your probability to be class 0 will be the power x0. X0 is the 0. Okay, it's this 0. Okay, the second term will be P1. Okay, this probability you will belong to class 1. Okay, but because it's also 0, but because we are belonging class 2. Right? So then the third term, okay, P3, P2, because we will have the product, three terms, okay? And then this time it's P1, okay? Right, so you can see this thing is really P2, right? This thing really, okay? Because this, anything to the power of 0 is 1, 1 times 1 again is 1, then 1 times P2 is P2, right? So similarly, if you belong to a particular class, and then you throw the one-hot encoding into this formula, okay? And you will get that class probability. Okay, so that's just a simplified way to write this joint probability. Okay, for each I. Any questions? All right, so again, we keep in mind we have this constraint here, okay? We have a constraint here, right? So the probability should sum up to 1, right? Now let's take a look at log likelihood, right? So we know that if we take a log likelihood, we take a log to this term, okay? And if we take log to this term, it becomes summation of log inside each term, right? And the x is to the power, and after taking log, x can be put at the front, right? X can be put in the front, log pi, okay? So this is, keep in mind, this is for a particular x. Now we have maybe n items, so we have another summation again, okay? So this is for n items, right? So the independent item. And this k is coming from this joint probability, right? This product take log becomes summation, right? Any
What
questions?
does that given theta mean? Where it says probability of x given theta?
Oh, I see. Yeah, so if you look at theta here is this thing, okay? Yeah, so you know, this theta is essentially this thing, okay? So basically, let's say this is a distribution n, okay? But the parameter is theta, right? Yeah, so this distribution basically says we have 20%, 30%, 50%, right? So when each time you draw a ball, right? So it's the color 0, color 1, color 2, right? So half of the probability will get 2, right? Next time you will still draw from this probability.
Is theta the collection of parameters, and is x
Yeah.
the
Theta is always the set of parameters. Theta means parameter. Okay.
so then x is the array of distributions, I guess.
X is which class you get, right? So this is maybe C0, this is C1, C2. I mean, it's not a class. I'm a little bit mixed. So X is basically these k possible values, which value you get. Okay.
So it's an array of multinomials.
Yeah, this is a multinomial distribution, right? So this is exactly what I'm talking. Okay. For example, if each time you draw a ball, right? So there are 3 colors, right? So red, blue, green. Red is 0, blue is 1, green is 2. Right? So and each one has a probability, and they sum up to 1. Each time you get a green ball with 50% probability, a red ball with 20%, a blue ball with 30%. Okay.
I gotcha. Okay, so x would be the set of all those balls as you draw them.
Yeah, exactly. So this x will be, I mean, the x here will be the set of balls. Right? How many green, how many blue? Okay. Yeah, if you understand it this way, I think that's more understandable. So yeah, in general, actually, this K will be for multiple class classification, how many classes you have. Right? So each data item has a label 1. Right? So if you have, since this one is blue, that one is green, right? So there are also features, right? But here we have univariate data, right? So we want to ignore those features. Right? It's too complicated to have multivariate right now. Okay? So this is called a constraint optimization problem, right? So because we have a constraint that has a probability each time you sample, right? So the sum should be 100%, right? So whether it's green, blue, yellow, right? So you will always sample correct. Right? Jointly, it should be 100%. Okay, so this can be solved using like large multipliers, like what we discussed last time. Okay, and we will show how to do this. Okay, again, the conclusion is very simple, right? So its conclusion is again this. Okay, so it's sample mean. So what does this mean? Let me give you some intuition here. Okay, so first understand the conclusion, and then we move ahead. Right? So this pi, this I is relevant to k. Okay, so three color balls. Right. So this pi, basically we have maybe p0 hat, okay, and p1 hat, okay, and p2 hat. Okay. So maybe let's say we have 3 balls, right? So the first ball color is 0, the second ball is 1, the third ball is 2, the fourth ball is again 0, the fifth ball is 1. By the way, this is 2. Okay, this is 2. And now, what's their one-hot encoding here? Right, this is one-hot encoding. This should be, let's say, this is x0, this is x1, this is x2. Okay, indicators. Okay, so 0 is basically one-hot encoding is 0 or 1 0 0. Right. So second is 0 1 0. Okay. The third is 0 0 1. Okay. The fourth again 0. So this is 1 0. The fifth is what? 1. So this is 0 1 0. Okay. Okay. Given these, what should be P0? What should be P0? How likely will draw P0? If in 5, what?
2 by 5?
2 by 5, yeah. So you see this is 5 times you only have 2 equal to 1. So this is 2 by 5, okay? 2 by 5. Right, so this is what we call sample mean. Why it's 2 by 5? Because n is 5, right? N is 5. 2 is basically if you sum them up, this column is 2, okay? Similarly, what is P1?
2 by 5 again?
Yeah,
Same.
2 by 5. Yeah,
Mhm.
yeah, because 1 is this, this term and this term. So it's the same. Okay. What is the P2?
1 by 5?
Yeah, 1 by 5 because it's only one term. So if this is 2, then summation of the third column is 1. Okay, divided by 5. And okay. So this is intuition. Any questions?
Professor, are we going to see the solution of the
Yeah, we
the
will see
minor-
how P hat is computed. Okay.
Okay, Professor.
Yeah. So anyway, so this is for the sample mean. Okay. Why? Why is this called sample mean? Right. So this is really, this is the mean, right? But this is a high dimension. Right? So because if you look at one-hot encoding, it's like in the previous example, this is 3-dimensional x, right? The indicator. Okay. So their mean is also 3-dimensional. Right? So if you look at the geometry in 3-dimensional, and you have coordinate x, y, z, then their mean value is something like taking every dimension to mean. Okay. So this is called skew sample. Any questions? If not, we'll switch to the derivation. Okay. Again, we have the note on Canvas. I think you can always refer to that. Okay. So we will have some assignment rather to this. Okay. So make sure you understand what we talked about here. Okay, let's come here. I needed the zooms annotation. Okay. Okay, so here, so basically we will have something like.
Professor?
Yeah.
We are seeing a review log document.
You're seeing note, right? So the Word document, is this correct?
No, Professor.
Let me try. Do you see it now?
Yes, Professor.
Okay, thank you. Yeah, let me know if I'm switching wrong. Okay, so it's just too many screens. Let me see. I can make mistakes. Okay. Yeah, so if you look at here, this page 14 is our slide page. Okay, so the duration is associated with the slide page name. Okay, so Lagrangian, last time we see, right? So this is the loss function we see earlier. Okay, we talked about it, right? So and so by the way, this is a log likelihood. Okay, we already take log, so this is summation. Okay, but we have a constraint. So constraint, we need to make it right hand side equal to 0. So even though this is equal to 1, but we need to make right hand side equal to 0. So we'll move things to the left. So the constraint becomes 1 minus this, right? And then this is the Lagrange multiplier, and this plus or minus doesn't matter because then there can be positive and negative, right? So you can adjust it. Anyway, okay. Now what you do is, previously we have what? We have p hats, right? So this is the previous parameters. Now we also introduce a new parameter, lambda, right? So what we need to do is we take a partial derivative to lambda and also to P1, P2, P3, and set all of them to 0. Okay, so this will work. So what we will do is we will do that in 2 steps. The first is take a derivative lambda, then we will take a derivative to Pi. Okay, if we take derivative P to lambda, what will be the result? Let's take it. Okay, so this term has no lambda, right? So take derivative 0. Okay, and if we take derivative of this term to lambda, it's a coefficient. Okay, it's a coefficient minor times 0. Okay, and the thing is that this after take derivative, we need to set it to 0, right? So this negation gone. Okay, so because it's in 1 minus something equal to 0, this basically this equal to 0. So we get this. So interestingly, we get back our constraint. So we do not get too much new stuff. It's just a constraint, right? But keep in mind, because we already encoded our constraint here, so this is an unconstrained optimizing problem, right? So we don't have the constraint of it. Okay, so we are just recurring this constraint back, right? So by taking the derivative. Okay, so this is the first thing. The second thing is that we now need to take derivative to the regular parameters, right? Not the new Lagrange multiplier. Okay, now if we do this, right? So if we look at this term, okay, these are constant, right? 1, 0, 1, 2, right? It's a fold code, right? So we are basically taking derivative this term, okay? And another important thing is we are taking derivative particular P0, P1, P2. Let's say we are taking derivative P2, then P0 and P1, these i's are gone, okay? We are fixing that, okay? Right. So another thing is that log Pi take derivative 1 minus Pi, okay? And this constant can go up. That's why we have this term. Right, so this summation is here, this summation is gone, and we have this term, right, and this is the constant. Right, so this is the left term, and let's look at the next term. Okay, if you look at this term, right, so we are taking derivative P. Right? So if you write it out, this first term is lambda, so a minus lambda, right? It's around P. So we were really looking at this term times this term, then take a derivative. And this is what? This is P0 plus P1 plus P2, okay? If we are taking derivative P2, for example, I equal to 2, then what we get is 1, right? So these terms are gone, 0, 0, 1, okay? This coefficient, okay? Right, so this term will be 1, but this negate, and lambda, right? Negate cancels. So basically we get lambda, right? So that's why we plus lambda. Any questions? Okay, so all we did is take a derivative to Pi, okay? We get this. But next, we want to set it to 0, okay? If we set this to 0, move lambda to the right-hand side, basically we're saying this thing should be equal to minus lambda, okay? And then, the Pi, can time Pi on both sides, then you get this, right? So this is basically, negation can go to, this is basically this. Any questions? Okay, I hope you are following the derivation. Otherwise, you can take a look at it and, offline, because the note is shared with you guys, okay? Now, how do we handle this term, right? So keep in mind, we don't have lambda yet, right? So this constraint has nothing very random. This has lambda, but for each Pi, we have something, right? So what we will do is after deriving this, we will take a break, okay? So what we will, and then we will take attendance, right? So after the break. So what we will do is we will summation I equal to 1 to k on both sides, okay? On the left side, you know that after taking summation, this Pi is 0. So the left-hand side is blank, okay? If we take the summation over the right-hand side, right, so this summation will go, right? Basically, this summation is, these two can swap, okay? These two can swap. So we just swap that summation inside, right? So the reason we want to swap them inside is because this term is equal to 1, okay? Because it's one-hot encoding, right? So if you have P0, P1, P2, right? 2 of them are 0, 1 of them is 1, Right? So if we sum 0 plus 0 plus 1, it's still 1. Okay, so this term is 1, so basically we get this thing. And this is n was summed together, it's a negative. Okay.
I have a question.
Okay.
How it is 1 that xi, sum of xil?
Yeah, so x is the one encoding, right? So this is 0, 0, 1, some are 1, 0, 1, 1, 0, 0, some are 0, 1, 0. Right? So if you sum them up, it could be 1. Okay. Right. This is k, right? So the first color, the second color, third color. Okay. This is for that particular data. That's for a particular.
For this k equals 3, right?
Yeah, this example k equals 3. Right?
Okay.
We can have 4. Then it's a different one. Okay. It's okay.
Okay. Thank you. Thank you.
You're welcome. So now we know that lambda is equal to negative n, right? So then we will come back. Right? So this is the negative n. Okay. The negation cancels, right? And then if you divide p n on both sides, you will get away with that. Right? So basically pi equal to 1 by n. So this term is what? This term is what we just described in our slide. Okay. Any questions? Okay, let's continue. All right, so yeah, so this is basically our derivation of the conclusion in our slide. So basically, yeah, let me see. I think I can scroll.
Professor?
Yeah.
Concavity, I mean, convex, how are we proving here anywhere, whether it's concave or concave?
Yeah, we will do that shortly. Okay, no, yeah. So this is basically the same we do. Okay.
Mhm.
So yeah, in the first 3 examples, we will really go step by step. Later we will. Right. So this actually is our result. Okay, so this is concave. Okay, why this is concave? If you look at so basically we want to show that this loss function is concave, like this error function, right? What in the world we have?
Mhm.
It's a little bit strange. This one. I think there's a bug. Okay. I hope this is that. Yeah, so yeah, basically we want to show this is concave, right? So this is really concave. It's not this. Sorry, I'm not sure why. So it's kind of yeah. Now it's kind of addressed. Okay. Yeah, we want to show this term is concave, and in order to do that, okay, so you just look at what is log pi. Log pi is concave. Is okay.
Okay.
Yeah, log pi is concave. Right. So log pi is concave, and the other things are constant, right? 0 or 1. Okay. Right. So it's a bunch of concave functions summed together. So this left-hand side is concave. Okay. And the right-hand side is linear. Right? So this pi are linear. x1 plus x2 plus x3. So linear is both concave and concave. Right? So then it's a concave plus concave. It's still concave. Right? So this function is concave. Is okay? It's just a summation of concave functions and a linear function. Is okay?
Okay, Professor. Got it.
Yeah.
Thank you.
You're welcome.
Will this handout be made available on Canvas?
Yeah, it's already on Canvas. Let me see.
Yeah, I haven't uploaded it yet on Canvas for our students, but I'll do so today.
All right, thank you, doctors.
Yeah.
Let me see. Yeah, my network is a little bit slow somehow. It shouldn't be so slow. I hope it can sustain us for this. Yeah, so basically, this is the slides, this is the note. Okay, you can take a look at it. Right. Okay, so next, let's look at the next function. Okay. Before that, let's take a break, a 10-minute break. Okay, and we will come back and take attendance, and then we will continue. But 10 minutes, basically 6:20. Okay, 6:20, maybe 6:21 or 22. Thank you. By the way, I will be here. If you have any question, you can ask me. Okay.
I have a quick question about assignment 2.
Yes.
So for the questions, should we answer inside the same cell that the question is in?
Yeah, if we have a cell, then you should complete it. But if it's not enough, you can add new cells.
Okay, that sounds good. Thank you.
You're welcome. Yeah, I will just put the attendance page here, so remind people who take attendance. Okay, after the break. Okay, let's begin. So I will sample some students, okay? Gahada. Gahada. Suman.
Here.
Okay. Pritesh.
Here.
Okay. Rashikesh.
Present, sir.
Okay. Tingchen.
Yes, I'm here.
Okay. Bhavana. Bhavana.
I'm here.
Okay. Muhammad.
I'm here.
Okay. Deepak. Deepak.
I'm here.
Pat. Pat. Adil.
Yes, I'm here.
Philip.
Here.
Jeremy.
I'm here.
Okay. Ahmad. Ahmad. Sandy. Sandy. No. I see chat. Just one moment. Okay, I see Sandy here. And Ronnie. Did I call Ronnie Asad? I'm
Here.
yeah, but I didn't call your name, right? So okay, yeah. If I crossed you, but you are actually here, just let me know. Okay. Clark Run.
Here.
Okay. Patrick Stankard. Patrick. Boniface. Boniface Singdala.
I'm here.
Okay. Amelia.
I'm here.
Okay. I see another chart. Just one. Patrick is here. Okay. Let me see. Patrick's here. Ziming Wan.
Yeah, here.
Okay. Good. Let me switch to the next list. Garat. Garat. No. Mingyong Liu.
Yeah, I'm here.
Okay. Staff Saeed. Staff Saeed. No. Yeah, so that's attendance, right? I see more students coming, right? So yeah, so okay, that's hopefully you will stay, not just because of the attendance, right? So let's continue. Right, so a little bit. Yeah, so next distribution we'll be looking at is normal distribution, right? I would say Gaussian distribution, okay? I think I probably should share screen in a different way. Yeah, so next is the normal distribution, right? So we usually use this this notation to describe, okay? With mean, mu, and sigma squared. Could we, you are not muted, so any questions? Okay, so For the Gaussian distribution, the probability density function is something like this, right? So I will not go into the details because this is just what you should know, or you just assume this is the case, right? So the Gaussian distribution basically has something like this shape. So shape like this, and the mean is the middle point, right? Which mu, okay? And actually, it's also the most likely point in terms of probability, okay? And sigma really defines whether your distribution is tall. No, it's a little bit ugly. So whether your distribution is tall or your distribution flat, okay? But keep in mind the area is always one, right? So if you're flat, means you have less concentrated in the middle, then you have more things spread out, right? So if you have something tall, then on both sides actually it's lower than this, right? Okay? Because it's PDF, so the area is 1. Okay, then let's look at log likelihood, right? So how do we derive this? Okay, so here we are having, let me enable pen again. Yeah, okay. So this is just one particular x, okay? Later we will see here, okay? So now we just look at one particular x, right? So we first take log over this term, okay? So what will be the log, right? So this will be log the first term plus log the second term, right? So log plus the second term, log is log base e, so with exponential, you cancel, okay? So the second term is really just minus this, okay? If you look at the next page, it's really this term here, okay? Now for the first term, let's look at y is equal to this, okay? That's good. So basically, so we want to compute this thing, take log, right? So this is actually easy to see, right? So if you look at this is 1 by something, right? So it's to the power negative, right? So and again, there's a square root, right? So square root is 1 by 2, okay? So this is really 2 pi, 1 by 2 to the power 1 by 2, okay? Times, this square and this square root can cancel, right? So it's really sigma to the power 90. Okay, so we are taking log of this term, right? So what's the result of this? Who can tell me? This is 1 by negative 1 by 2, right? Because the log to the power of something moves to the power of something to the beginning, right? Log 2 pi, okay? Plus, okay, plus, but plus log this thing, but this is negative, right? So this should be negative. Minus log sigma. Okay? So this is basically what we have. Now keep in mind this is just one item, yeah, right? So if we have n items, so this will be n of this constant term, and this is also n times this log. Okay. While this thing will there be n items, but they are all from the same distribution, which means the sigma is the same. Right? So basically we are adding summation over this. Okay. So this gives you the next page. Right? So adding summation. Adding summation of this term because we have XL, right? So it's the system is what we just derived. Okay. Yeah. So now what will be the likelihood estimate, right? So the XL is what you see. Right? Then you can compute this value, compute the log likelihood. Right? You want to find the mu and the sigma that maximize the likelihood you see X. Okay. So we will show that you should put mu as this value. Right? This is sample mean. Right? So this time it's a Gaussian distribution. Right? So which means it's a continuous distribution. It's unlike before. Okay. Let me see. Assume your end line distribution is something like this. Right. So this means when you observe those x, right? So this x value could be from, let's say, 0 to 10. Okay. You will see a lot in the middle, like 6, 7, 8, 5. You are not likely to see 9 and 1. Right? It's less likely. Okay. So you see these values. These are continuous values, maybe 5.5. Right? So how to estimate the most likely mean value of the distribution? Right? So this is sample mean. Okay. Just take these values you see and take them. Right. And similarly, this is sample variance. Right? So you can take these values you see and compute the variance. It should be the variance of the Gaussian distribution. Okay. Any questions? So again, this is what we call the ML estimate. Okay, ML estimate. So this means, let me change the name. This basically means that these two values are derived by maximum likelihood estimation. Okay, we will see how we derive this now. Okay. Oh, I see a chat. Pat is here. Okay, let me see. Xiaohong, I think that is fine. So we didn't cross it. Pat, let's see. All right, so let's begin. Let's move to the note. Okay. So let's recap what we see. Right. So basically we are using this probability, this requirement. Okay. So you know, square root. So one thing we are a little bit different is here. Okay. So okay. So one thing we are a little bit different is theta 2. Okay. In our case, theta 1 is our mu. That's the mean. Okay. Theta 2 is our sigma squared. Right. So remember here we actually have sigma squared. Only one sigma, right? So this is sigma squared to the square root. Okay? So this is the same function, Gaussian distribution. Okay, and then this is our joint is log like this is likely. Okay, this is not taking log here. So because this is product. Okay? And so yeah, after taking likelihood, we work at this. Right? So this is what we get on our slide. Okay, hope you. Yeah, okay with this. So one difference is here we have log sigma, right? So this is 1 by 2 because this is sigma squared, right? So, and then this thing can become 1 by 2. Right? So they cancel. Right? So they are the same thing basically. Just want to convince you they are the same. Now this is our log likelihood, right? So what we want to do is, so we want to have our parameters sigma, you know, the variance, the mean. We set each of them, take partial derivative to 0, partial derivative to theta 1, for example, and set to 0, and then take partial derivative to theta 2 and set to 0, right? So let's take a look at what will be the result. Right? So first we take partial derivative to theta 1, okay, and what will be the result? Right? So this term has no theta 1, okay? These two terms have no theta 1, they will be gone, okay? Okay, so these two terms have no, so we only care about this, because only this term has theta 1, okay? So if you look at theta 1 here, right, so, you know, what we can do is we can treat this whole thing here as one particular variable, right? So then it's a constant, 1 by 2, right? So 1 by 2 will come here, okay? 1 by 2. I don't know why the pen doesn't work well. Let me try to. So this thing minus 1 by 2 actually comes here, okay? Including this minus. I think it's because of some network delay. And now let's take a look at this term. This term, if we you know, summation, we can put summation here, right? So we consider this x minus theta I, theta 1 as u, right? So then we have partial derivative of u squared to u, right? This is 2u, okay? This is twice u, okay? So then next we will take a u to sigma 1, okay? And because sigma 1 has coefficient negative, so this is negative, okay? So this is how we go from taking partial derivative here, right? And now these two which is basically this 2 cancel here, this 2, which comes from this. Okay, and negate cancel with this negate, right? So this basically says we have summation of this equal to 0. Okay, and if we consider this summation I equal to 1 to n. Okay, and this is n theta 1 minus. Okay, so this is minus n theta 1. It's the same thing. Okay, this xi has superscript I. So something like this. And if we set this equal to 1, basically we say these two are equal. Or we divide by n, we say that theta 1 equal to the mean value. Okay. This is a very very interesting result here that you can see is this. Okay, so you can see that it's around this theta 2. Right? So even if you just take partial derivative theta 1 itself, right? The result is not a function of theta 2. It's around theta 2. What this means is that for any theta 2, taking this mean always makes your value the maximum. No, the maximum. Okay, so this is an interesting conclusion. Around this theta 2, although we are not marginal, we are not eliminating theta 2. So this is one conclusion. Okay. And so another thing that you need to, yeah.
Can you repeat the conclusion once again?
Can you repeat your question?
Can you repeat your conclusion once again?
Okay, so we are taking a function with two variables, theta 1 and theta 2, right? Taking partial derivative theta 1, okay? But theta 2 is delimited. It's okay, right? Theta 2 is not here, right? Because this term has no theta 1, it's cancelled. It's 0. Take derivative. Okay? This means for any theta 2, this is the best value for theta 1, okay? It's independent of theta 2. It's okay?
Okay, Professor, got it.
Okay. Another thing you need to pay attention is this is a quadratic function, right? So this is equal to theta 2, theta 1 minus x squared. Okay, x is a constant value. Okay, this is I theta. Right. So this is more like a x minus a squared. Right. So this is a convex function. Right? You should know this. Right. So this is a convex. Have a minus, it's concave. Okay. So basically, this is a concave function, right? And this is the best one. Okay, the maximize this one, right? If we ignore theta 2. The reason we can ignore theta 2 is just explained, right? Now, next we want to take partial derivative theta 2 and theta 2. Okay. So this is where things can get a little bit complicated. Okay. So let's take a look at how to do this. Right. So firstly, if you look at the theta log theta 2, right? So this term has theta 2. This term has no theta 2. We can eliminate it. 0. Basically. This has theta 2, but at the bottom. Right? So basically, if you first consider this term, theta 2, it's log theta 2, take a derivative theta 2 is 1 by theta 2. Right? So this is why we have this term. Okay. This theta 2 is at the bottom. Okay. And for the second term, this term, let's think about this term. Okay. Take derivative theta 2. Right. So yeah, I think there's some network delay. That's why writing is not working. Okay, so for this theta 2, the first thing is we should know, this is theta 2 negative 1, right? So this thing, okay. So we know that if take a derivative, theta 2 negative 2, okay. And for the other terms, like those, they are constant in terms of theta 2, okay. Because when we take the partial derivative theta 2, theta 1 is treated constant, okay. So basically, we are saying these are constant. Okay, and this is negative 1 by theta 2 squared. Okay, after taking derivative. So this will give us this term. Okay, theta 2 squared at the bottom. This will become plus because we have negative and cancel with this negation. Okay. Now what we need to do is set this to 0. Right. So if we set this to 0, okay, basically you can time both sides with with 2 theta 2 squared. Okay. On the right hand side, 2 0. Right? On the left hand side, there's a 1 theta 2 here. Okay, and this theta 2 cancels. So this gives you this result, and then you know, this, you move this thing to the right-hand side, right? So this becomes n theta 2 equal to this thing, and then divided by n on both sides, you get this value, okay? And keep in mind that theta 1 is what? We already derived. Theta 1 is the mean, okay, sample mean, right? So this is really sample variance. Okay, this is how sample variance is defined. Right? So if you have the mean, then your bias, your different, for each data item you see in the Gaussian distribution, samples, right? So how far away you are from. Right? So then, you know, you square them, sum, and take the average. Right? So this is the average squared bias. Okay, so this is the cross variance. Okay, so this is the estimated theta 2. So this basically proved our conclusion here. Okay, but one thing remains, right? So you know, so one thing remains. Right? So we show that for any theta 2, theta 1 is really the maximum point. Okay, but now how do we know this theta 2 is the maximum? Right? So one important thing you keep in mind is theta 2 is a unique value. Right? We don't have too many extreme points, only one theta 2 point. Okay. If this you agree, then next let's look at the value. Right. So theta 2 is sigma squared. Okay. Theta 2 is equal to sigma squared. What's the range of this value? Who can tell me what's the range of this value? Yeah, it's from 0 to infinity. Okay. To infinity. Right. So you know it's a variance. Okay. So let's take a look at the extreme cases, two extreme cases. Firstly, what if the theta 2 is 0? Right? So what if this is 0? Okay, we know that log is of this shape. Right? Your theta 2 can get infinitely close to 0. Your y will be infinity. Okay, negative infinity. So let me see. Yeah, so basically we say that this value will be, oh, this is negative infinity, but this is infinity. Right? So basically, you know, but actually this dominates, okay, because this is kind of like exponential, right? So it's jumping fast, okay? This dominates. So on the other hand, if you look at the positive unity side, right? So this thing goes to 0, okay? If it is positive unity, this thing goes to 0, right? And this thing goes to infinity, okay? So if the positive infinity, you know, log theta 2 goes to infinity, and this divided by infinity goes to 0, right? So the total value, you know, is negative infinity because there's a negation sign, right? If you have very close to 0, you can also show that by taking a limit, you can also show, because the speed is different, right? So you can also show that it's gonna go to negative infinity. Okay, so therefore on both sides they are negative infinity, and you have a concave value in between. Okay, so and you have only one extreme point, right? So if you only have one extreme point, that means this value is really theta 2 here. It's really the best value. Okay. Yeah. So for the details you can derive yourself, but basically that's the idea. Okay. Any questions? Yeah, if not, let's continue. I think.
No, I was gonna ask what, you know,
Yeah.
theta 1, theta 2, are those the extreme points in the X object?
No. X comes from a Gaussian distribution with mu and theta, sigma square. Okay. It's a sample from this distribution. This is X. And these, let's say we have n such xi's we see, right? So what we talk about the 1 to 10, we see a lot of 5, 6, 7, okay? And the 4, we don't see a lot of 2 and the 5, 9 or something, okay? So these are the xi's. It's okay? And they come from maybe a distribution saying that, hey, mu is 5 and the sigma square is maybe 1 or 2. Right, so these are the parameters.
Okay. And what do the theta 1 and theta 2 represent?
Theta 1 is mu, theta 2 is sigma squared. Okay.
Oh, okay.
Yeah, so this is what we just described because of the notation. No. So if you look at here, this theta 2, theta 1, theta, this is theta 1. Okay, this is theta 2, right? Theta 1. It's okay?
So the purpose of this, we're trying to estimate the
Yeah, we want to
mean
find
and
this.
the
Yeah,
variance.
yeah, go ahead.
The purpose is to estimate the mean and variance, the mu and the sigma.
Yeah. We want to find the sigma 1, theta 1, theta 2 that maximizes L likelihood. Okay. This likelihood is the likelihood you see those X values, right? 5, 6, 7. It's okay? Yeah, if you cannot catch up, maybe you need to spend some time offline, okay, because you have close to 100 students. So, okay, if a lot of you are not catching up, we can stop for you. Okay, so let's continue. All right, so so far we talked about the estimation, right? The estimator, maximum likelihood estimator. Okay, so the estimator actually may not give you the best result, right? So here we assume the true theta is the ground truth theta, right? A sigma square mu. Okay, so this ground truth theta you want to estimate, right? For your estimator, we treat the estimator as a random variable, right? It can be any of those cross. Okay, right? So but the estimator itself, you know that the mean value of the estimator is here, right? So this is called a biased estimator. So hopefully most of the time we want an unbiased estimate, which means if you take the average value of the estimator, the mean of the estimator, it's exactly the ground truth parameter. Okay. Another thing is that your estimator may have a variance, right, depending on your x1, x2, x3 you see. Okay, it's a variance. Right? So the variance, we want the variance to be as small as possible. Right? So we want to finally our estimated a particular d, right? Because this d is actually theta's estimation, theta hat. Okay. For a particular data set x1, x2, x3, we will have a particular d here, right? So we hope this d, this theta hat will be close to theta. Right? So we don't want to have a very big variance. It's okay? Yeah. So we want to estimate a parameter theta. And so our estimator from your samples, right, a particular sample, this is actually n data point, right? But because we can have different training data, right? So different set of training data give you a different I, okay? And for each training data, we will have our maximum likely estimate with DI, okay? Because the training data can be a little bit random, right? So this time you get 1, 2, 3, 1, 2. Next time you get 2, 3, 1, 2, 3. Right? So there are different sample from the underlying distribution. Right? So your estimator theta hat or DI can have very different values. And so what we want is actually the bias, which means the expected value of your estimator from all kinds of data, right? Your sample from the data underlying data, right? Should be as close to as the theta itself, right? So ground truth theta. Okay. So bias is defined as the distance from your expected, theta hat, right, to the theta. What's the difference? Okay. And we also have a variance. Okay. So the variance is, if for different training data set sampled from the ground truth, right? So how likely your estimator, your theta's hat will have the variance. Okay. So we want the variance to be small, which means as long as we have this xi's, even though there are some data items that are different, but the estimated theta will not be too different. Okay, it's relatively stable. And here let's consider a error metric called the mean square error, right? So basically we say that we are using this, right? So for each data item set, right, of training data set x1, right? So this x, we are not talking about one particular data item, we talk about a set of items. X1, then we get a d1, okay? And d2, d3, right? So we want to compute the mean square, right? So we have d1 minus theta d2 minus theta d3 minus theta. We have the square and we divide by 3, okay? So this is what we have, right? And so this is one error metric, okay? So how wrong our estimation is going to be from the actual ground truth feed, right? And we can show that this error can be decomposed into two parts. One part is bias squared, okay? The second is variance, right? So bias is linear and variance is squared, right? So of course bias, if you want to be at the same level as the variance, which is squared, okay? So it's bias squared plus variance equal to error. So for the same error level, there's a trade-off, right? So if you want a more, you want a unbiased sample, right? So there's no bias, okay? Then it means your variance could be a little bit larger. Right? So different times you will have it for different xi training data set, you will have different theta hat. Okay, but when you have enough of them, maybe you have tried a 10 training data set and you take the average is quite close, or there's unbiased estimator to the ground truth. Okay, so this is called variance, right? And the bias means each time when you have a training data set, each time how likely you are far away from so this, right? So variance, it means for different theta hat, right, on different those 10 theta xi's, okay, how likely they are different from each other, okay? We want them to be as close as possible, right? So you don't want to say, let's say, we know that the theta values and the average value is 10, right? So the first time you guess its value is, why? It's a bit weird. It's kind of losing control. Just want to try to, yeah. Okay. No, it's so, for example, if your average value of your data item is, let's say 10, okay. Unbiased means this time you get 15, next time you get 5, another time you get 15, another get 10. You assume it's 5. This is unbiased, but the variance is big. Each time you have a difference of 5. Okay. And so this is what we call the variance big, but it's unbiased. Okay. Another extreme is that you have a small variance, but it's biased, right? So each time you guess 11, 11, 11, 11, right? So it averages 11. It's different from 10, a little bit biased from 10, but the variance is small, right? So each time you are not far away from the value by 5. It's just far away by 1. Okay. So this is there's a trade-off between these two. This is what we want to see. So how to show this, right? So how to show that this mean squared error is equal to the bias square, right? So this is bias, right? Expected theta hat value to theta, right? So the ground truth value, okay? This is bias square plus the variance. Variance is, this is the DIs, different DIC. So this is variance of the different time you train your data, right? You fit different data set, how likely you will get the theta parameter. Okay, let's take a look at the proof. Yeah, let's take a look at the document here. Yeah, okay, let's continue. Yeah, the proof is actually quite simple. So there's one small trick though. Okay, so let's take a look at it. So again, let's come back to here. Okay, so we have a mean square error of our each time we fit, right? We get right? So and the variance plus bias square. Okay, and the random variable is this way. Okay, because your training data may be random. Okay, this time you get, let's say your ground truth data is 100 of them. Each time you get 20 of them for training. So there's some randomness. Okay, and here, this is our mean square error. We just explained why this is the case. right? So we want to show that the mean square error is actually, equal to this. Right? So how do we prove it? So the first thing you want to do is minus something and plus back something. Right? So they are still equal. But what we do is we construct this term, the expected theta hat, okay, and sum back. Why we're doing this? Right? So if we do this, then we will get two terms basically. Okay, so we'll get A.
Hey, I got a question.
Yeah.
The theta hat is the sample variance and the theta is the actual ground truth variance. Is that correct?
No, this is not correct. So we are talking about this. Let's say you have training data x1, x2, x3. Okay. Then you have f theta. Okay. Now you are calling your model fit. Okay, fit theta. Right. So this will give you theta 1 hat. Okay. This could be, for example, Gaussian distribution. This is equal to mu1 sigma 1 square. Okay. This is fit on the second data set. This theta 2, this second. This. Is this okay?
Yeah, that's cool.
Okay, yeah, so this is what you are. Right, so for different training data set, your estimated value, maximum likely estimator may not be the ground truth. Right, so there's some variance and bias. Okay, so now because we minus something and plus something, right, so then we can have this A, this B, A plus B squared, A squared plus 2AB plus B squared. Right, so that's what we are doing. A squared plus 2AB plus B squared. Right? Yeah, the nice thing about this is because then we get the variance. So expectation, linearity of expectation say that if you have x plus y to random variable, unconditionally it will equal to x plus exponential expectation. Okay? So this is always holding. Okay? There's no constraint. And like variance, you need x and y to be independent. Okay? So then we can take this e to each of these terms. Okay? And if we look at the first term, this is exactly variance. Okay? So we already constructed variance. Right? Now let's look at the second term. Right? So the take expectation, this 2 will be constant. Okay? And keep in mind, so expectation of random variable is a constant. Okay? And this is a constant. But theta is also a constant. It's ground truth theta 1. Okay? So the only random variable is this. Right? So then we can move those constants 2 and the second term. This 2 and the second term are constant. We can move them on. Okay, we then take the expectation of this term. Okay, which this is a random, right? And for the third one, this ground truth theta is a constant. Right? Expectation is a constant. So this whole thing is a constant. So this take expectation is gone. So we have this term. Now let's look at this part. Right? So this part, because this is constant, right? So take expectation is 2. Right? So this expectation of this variable. Right. So nice thing about this is this term is 0, right? Because this thing and this thing are the same. Okay. So 2AB is gone after constructing this. This 2AB is 0. Okay. That's why we only have the first term and the third term. A squared plus B squared. Okay. And this is bias. Right. So this is expected theta hat. Right. So this is the ground truth theta hat. If you try different times, your expectation is the value. The ground truth scan. Then it's a biased estimate. Okay. You never get the true value, but it's close enough. The variance is that's fine. Okay. Any questions?
Professor, I have a question here.
Okay.
For each sample, there will be theta hat, right?
Yes.
According to the understanding, yes, right? Then, but maximum likelihood estimate gives for all the value, for all the samples, right?
Yes.
For all the samples, it gives one theta value. Here comes my doubt. How do I interpret theta hat and theta? And,
yeah, for example, let me give you
expected value.
Yeah, for example, if you have a hand-rated data samples, okay, each time you randomly sample 80 to get x1, next time you randomly sample 80 to get x2, randomly sample 80 to get x3, right? So this actually, you know, you can easily do this, right? So you can see, for example, let me stop here. So I believe you know, our training data, each time you don't get the same training data. So you should know that there's a trend test split. So I'm not sure whether in the sum you will see it, but basically, you know, you want 80% to be training data, 20% to be some, you know, the test data, right? But it's not always these 80% data, right? It's not always the first 80%. Right? It's a random, okay? For example, if you look at there's a random state, okay? Maybe this time you will get to the, you know, let's say we have 5 data points, 1, 2, 3, 4, 5. This time you get 1, 2, 3, 4. Next time you get 2, 3, 4, 5. Another time you do trend test split, you get 1, 2, 4, 5 as trend. Okay, so these are the x1, x2, x3. Okay, right. So after doing that, you can model the fit. Right? You get theta 1 for the first training data, get theta 2 for the second training, get theta 3 for the third training. Right. So then the average is the mean. Okay, and you see whether it's unbiased, whether the average should be expectations and should be seen. Okay, the branch truth distribution. Right, and these themselves have some value. Right, if you change a little bit of the training data, right? Let's say you swap out a training data set, right, and swap in one test data to here, and your parameter changes a lot. The model is not desirable. It's not stable. Do I answer your questions?
Yes, Professor.
Okay.
But can you give, I understood this example, but I'm also interested in getting the intuition behind the normal distribution as well. Let's say we have a population normal distribution, we have got a sample. Can you give me intuition in that side of angle, if possible?
Yeah, I probably will leave that to TA because, you know, here we are not talking about any particular distribution, right? So you know, this is a normal distribution. This is a multinomial distribution. We have 3 distributions for all of them. This whole, okay. This is proved from expectation variance. You know, probability theory. There's nothing relevant to a particular distribution. Basically, this holds for any distribution. Okay. It's okay. Yeah.
Okay.
If you want to look at a particular distribution functioning, then maybe you can go through an example yourself or to the TA. Right. So the derivation basically is the linearity expectation. Okay. That's all you need. Any questions? But the takeaway message is just this: right? Bias square plus variance is your mean square. Okay. This is what you need to remember. Okay. Any other questions?
I guess.
Yeah.
What if you had a case where you didn't know the ground truth data? Well, I guess could you estimate it with the bias squared plus variance?
Oh, actually, the theta, we assume it's correct, right? So you know, we have seen that it's never correct, right? So it's just you have useful models, right? If your underlying distribution very close to Gaussian, and you assume this is a Gaussian distribution, then you will get a good result, right? If it's a Gaussian, then you assume it's exponential, like Gaussian is something, then you will get a very bad result. Okay, so this is here we assume the ground truth is truly Gaussian, generic process is truly Gaussian. Then how you can fit in there, right? So just like in the regression model, we have a sign, then we put normal to fit. Okay, so it's never going to be a correct model. It's just a useful model. To answer your question, so this is your inductive bias. This is assumption. Right? So you have a clear distribution that parameter theta. Okay, if your assumption is wrong, your model will not work. Okay,
I think so. So we have a set of data, and we're assuming the entire ground truth set of that data is a Gaussian with a sigma and.
Yeah, exactly. So here there's nothing relevant to Gaussian. Okay, here we only have expectation and variance. Okay, the expectation for any distribution you can take expectation, right? So, for example, if you look at, let me see.
Right, so you could apply it to other distributions.
Yeah, exactly. This
We're fitting some known distribution to a data where we have some samples, but yeah.
Yeah, for example, if so for different data you need different distribution. For example, if you think about your data is almost always centered around this value and very unlikely to center around these other values, maybe Gaussian is a good choice, right? Another example is, for example, if you count, let's say, how many people publish papers, right? So maybe in the graduate school, maybe most people publish 5 papers, less than 5 papers, right? So some excellent students publish 30 papers, for example, right? So this distribution definitely not Gaussian, right? So it's maybe exponential or something, right? Gamma function, okay? Right? And then if you assume it's Gaussian, right? Everyone should have published 15 papers in the middle, right? Then probably the graphic model will not work, okay? So we are assuming any distribution, right? And even here in the previous examples, we are just looking at the 3 toy examples, 3 distributions: normal, multinomial, and Bernoulli, okay? But there are tons of distributions, right? So the exponential distribution, gamma distribution, Dirichlet distribution, okay? So we cannot go through all of them. We are just illustrating the idea. It's okay? But for any distribution, this thing holds, okay? This is the bias variance trade-off, okay? Do you answer your question?
I believe so, yes. So we're picking the model that fits the data, and then we can use samples from the data to find out the sigma and the parameters of the model.
Yeah, exactly. So basically, in your model, you need to define your input, and like in graphic model, what are the factors, right? And then what will be the good conditional probability, right? So here Gaussian is the kind of conditional, if you come to C1, what's X, right? And this is the modeling part, right? This is why you need someone know machine learning and know the data, right? This is the technical part, right? So what we are teaching is how you go along each edge to do the estimation, right? But how to construct a model and make it work on your real data set, right? So whether this model is more meaningful than the others, whether I should choose a Gaussian distribution or exponential distribution, that's something that you need to work out. It's okay?
Yes, thank you.
You're welcome. All right, so yeah. So next is the Bayesian estimation, right? So the difference is that, previously we assumed if we see X, right, so we want to find the most likely theta, right? And then we assume the theta is just the ground truth theta. Actually, it's theta hat, right? But we will use that as a ground truth theta, just like the model fit, right? So then we will assume it's trend, and then we use this theta to generate new data, okay? Bayesian estimation is safer, okay? So we will treat theta as a random variable, right? Just like what we said earlier. For example, let me see. So am I showing the right screen? Okay. Right. Let's assume this is your theta, and this is your likelihood, right? I see a chat. Yeah, Sandeep is saying, but unfortunately, if you're telling me so late, I cannot come to you. Okay, so let's say this is the theta, right? So, and this is the loss function, right? So we wanna, this is probably the best theta, okay? Maybe 10% probably, okay? But this theta is 9.9% probability, right? So it's not too bad, okay? But we are totally ignoring the probability here, right? In maximum likelihood estimate, we assume this is the theta, and then using this theta, we assume the distribution, right? But if our theta is here, let's say a Gaussian with a little bit different mean, right? So what will happen, right? So basically, we should have, let's say, a weighted sum of all the cases. Let's say for this case, probably maybe 10 points, right? This is 9.9 points, right? So this is safer. We consider all possible thetas, just like here, it's not so likely, right? If this theta is not so likely, then, then probably we should give it a very small weight when of the probability we see the data x. Okay, right. So if we consider all these thetas, this is called the Bayesian estimation. Okay, so this is what we are looking at. So put simply, in the case of, let's say, so Bayesian estimation, what we are doing is we are having a posterior density of theta, right? So usually we will assume that you already have a prior estimation of theta, okay, right? So for example, if you talk about a group of students in our class, what will be the height? Let's say for male, right? So maybe 1.7 meters, right? So something like this, okay, right? This is your prior belief. Then if you come and you see, oh, these people, right? So you see these x, okay? You see these people, they are all very tall, all 1.8, 1.81, 1.82, right? So then it will change your belief, right? So maybe the mean in this class is not 1.7, it's 1.82, right? So something, right? So this is, you know, the prior and the posterior, okay? And this is the data. This is generative probability, right? So for a particular height, and you assume the class should be a Gaussian distribution among the height, right? So for different people, okay? Then we'll, you know, how likely we'll see this height if the average is 1.7, right? So 1.72 is maybe this probability, okay? Something like this. But keep in mind, this is the theta itself can be a function, right? So we don't believe it's 1.7. Maybe it's 1.6, most likely 1.7, and it jump. Unlikely 1.8. Right? So the piece theta itself can be a distribution, right? Any questions? Yeah, so this is basically the base formula. So, you know, previously we said this thing can be represented as summation, okay? Summation. Now, because the theta is you know, continuous, we use the integral. Okay? Basically, it's the same thing. Consider every possible theta. Now, if we use the previous way of estimating this theta, right, the posterior, right? So what will be, so keep in mind, this posterior p theta, we assume we already estimate like this. So it's here, okay? If we assume this, right, so then how can we use it for different purposes? The first purpose is for density estimation, right? So like what we have done before, density estimation. How can we do that, right? So we can have this formula. We take integral. Okay. So how to understand this formula? Right. So let me give you some example. Okay. So first, what are they? As we said, you can ignore the condition. Right. This is like the fourth set. Right. So like your union set of x. Then it's a p theta times px condition on theta. Right. So these two gives you a joint probability x and theta. Right. But because you are under this condition x, so this has a condition x at the end. Okay, so this is what we have here, distribution. Right. So put simply, if you have this on the condition side, it still keeps in the condition side. Then you just look at px condition theta times p theta, which is px and theta both have a condition. Right. So and then you marginalize out theta by taking integral. This gives you what? You marginalize this and this gives you this. Right. So this is just saying, hey, if you look at, you find all these data sets you've seen right now, okay? And assume a particular distribution. Right. We still need to have the distribution assumption so that we can take it, okay? Prior shape and posterior generative probability shape. And so if we assume this, then we take integral, we will get a more safe estimation of x. How likely we will see a particular x, right? So as a density, okay? Given the data you see. Right. So we are marginalizing of the theta. Okay. And one particular assumption we have been assuming is that this term is actually equal to this term. Right. So we assume generative probability. Right. Once your model parameter, distribution parameter is set, your probability for x is fixed. It is independent of x. The data you see. Okay. So you can eliminate. Right. This is using our, if you look at the graphic model perspective, just say x is used to estimate theta, right? And then theta is estimated. Okay. So you don't have this link directly. You don't need it. Okay. And yeah, so this is for density estimation, right? So which means the y is the probability, okay, for each possible value x. Okay. Now, if we consider regression, right? So regression previously what we do if we use maximum likelihood estimation is something like this, right? So we find the most likely theta hat, and then we put the theta hat into the maybe polynomial function and try to see if I see a new feature x, what will be the y, okay? But that's again not safe. Right? So we want to consider all possible thetas. It takes integral, right? And the probability associated with that is this probability. Right? So this thing we can estimate from here. Okay. So then if we play safe, we take expectation over all possible thetas. This y is obtained from 4 base sample. Okay. But you can see that it's quite complicated, right? So you need to assume a prior distribution, and you need to assume this p is straight, right? And this p is straight, and then you can take the integral, okay? And then just to compute this. This is often too expensive to compute, right? Especially integral is very expensive. Sometimes something cannot be easily integrated, right? So there's no closed form formula, okay? You have to use numerical methods sometimes. So oftentimes we will find a middle ground, right? So not so something like MLE, right? Maximum likelihood estimations. Just consider particular theta, right? So for Bayesian is taking all theta, but you take the integral, right? It's too expensive. We want to find the middle ground, okay? So the middle ground, because evaluating the integrals is computationally too expensive, okay? And we will use some other method. Right? So this method is called the MAP, okay? Maximum a posterior estimation, okay? So what does this mean here, okay? Here you can see that, so this is the posterior probability, right? After you see x, what's the most likely value, what's the most likely theta, right? So you want to find the most likely theta here, right? So this looks like a maximum likelihood estimation, right? So what will be the difference, right? So once you have the most likely theta, this is still point estimation, right? So then you can use it for density estimation, just use this point, right? And use this point for regression, okay? Just like a maximum likelihood estimation, right? But what's the difference for MAP and MLE? What's the difference? Anyone knows?
Given theta, what is the probability of it being x? I mean, it gives the theta and then tries to fit the given data.
Yeah, so but the MLE is also find the theta that maximum the likelihood. Right?
No, but here we are giving the given x, given data, what is the probability of theta? Over there, given theta, what is the probability of it being likelihood? We are calculating their likelihood, right?
Yeah, it's still the likelihood, right? So how likely? Right. Yeah, so the reason is this, if you want to see the difference, actually the difference is that the shape of these two variables are reversed, okay? Right. This is a, this is a posterior belief on theta. It's not in maximum likelihood, we are considering the most likely data we see, right, for a particular theta. Here we see this data, but we want to find the most likely theta, considering all possible thetas, right? So maybe this is a little bit confusing. Let me go back to a previous slide. Here, okay. So maximum likelihood is argmax theta for this thing, the generative probability, okay? Well, map is maximum likelihood of this, right? The difference is what we consider the prior or not, okay? In maximum likelihood estimation, we only consider this part, assuming this thing is the same for all, in all cases, right? It's a uniform distribution, okay? So basically, we don't have any prior guess of theta. Let's say, what's the height of people, right? So you have an estimated guess, but here we are assuming from 0 to maybe 2 meters, they are equally likely, right? So you are not using the prior belief that you can use, okay? Well, here in map, this method, you can integrate the prior distribution. Okay, so this is the key difference, right? You are still finding theta to maximize the probability, but previously you just consider this probability. Now we also need a prior. Okay, so that's the key difference. You can integrate your prior without even seeing the data. Any questions? Yeah, so just want to make things clear. Okay. All right, let's see whether we still have enough time. Yeah, so don't confuse it with another metric, right? So there's another metric also called MAP, right? So called the mean average precision. So for object detection, for example, it's probably used. But mean average precision is yet another matrix, right? Scikit-learn also has something like this, right? So it's a middle ground between precision and recall. Okay, true positive or false positive. It's again something like, you know, Y true and Y score, right? So just yet one of the many other, you know, like F1 match or something. Yet one of a bunch of those kind of metrics. Okay, so it's also called a MAP, right? So, but usually this is used called MAP. Okay, that's not used. So here, if you talk about maximum posterior a posterior probability, right? So that's why we call posterior. Okay, right? So we have the prior, then we have the posterior. Okay, we have all uppercase notation, right? So that a comparison. But if we have the
we are seeing your
what? Oh,
Professor, we are seeing your PPT screen.
I see. Let me. Yeah, you need to. If next time this happens, like. So basically, you know, for MAP we have all uppercases, maximum a posterior because we have the prior. Okay, and there's another metric called the mean AP, MAP, mean average precision. So if you look at object detection, this is used a lot, called AP average precision. And then you take a mean average precision. Usually the M is in lowercase. Okay, they are totally different. Okay, and this is yet another, you know, yet another matrix. For example, in second, you can have this. Right? So you get the Y true and Y score. Okay, then this is just like F1, you know, and AUC score, something like that. AUC curve, it's kind of okay. F1 measure, precision recall. So, for example, if you look at the yeah, basically you have, it's just one of the many metrics that we have. Precision recall or something simple. Okay, true. Right. So this is in object detection. Actually, we have multiple objects. That's why we don't have just the average precision. We have the mean average precision. Mean is taking over basically all classes. So each class is considered as a binary classification, right? Whether it's a cat or not, whether it's a dog or not, etc. Okay. Just a side note. Don't confuse with mean average precision, because this is you know, max a posteriori estimation. Okay. All updates. Okay, yeah, so here's the difference, right? So maximum likelihood estimation, we'll summarize this and we'll derive next time. Okay, maximum likelihood estimation basically is, you know, theta, and we want to maximize the data we see X using a particular theta. That theta is what we train, okay? And the Bayes estimator is saying, hey, we will take integral for all possible theta, even though the theta is not most likely, right? It's also there's some likelihood. We also need to consider that, okay? So, and MAP is basically reverse these two, okay? So that's the MAP now, okay? And here's example. Let me see whether we still have the time. Okay. Yeah, maybe we will continue next time. So this example will be quick, actually, very simple. We will continue next Monday. Right? So yes, that's the end of this class. Okay, any questions? If you have any question, it's time to ask. Thank you. Because it will take more than 5 minutes to derive it. So I don't want to go past the time.
Thank you, Professor. It was a nice class. Thank you.
You're welcome.
Thank you very much. Have a nice day.
Thank you. You too.
Question about the assignment deadline, Professor.
Assignment deadline is just Friday, right? So let me check.
Friday. Can we get few more days? Would it be
Okay.
possible?
So yeah, let's be consistent. To be fair, let's make it next Monday for all students, right? Because if I make exception for one student,
well,
need to be fair for all students, right? So otherwise, other students.
Okay, thank you.
Right.
Thank you. That's nice.
I will update that in Canvas. Okay. Yeah.
Okay, thank you.
You're welcome.
Thank you so much.
You're welcome. Okay, if you have no question, I will probably end this class. Last minute, okay.
So I have a questions about submission of the assignment 2. So we just when we run the cell, so we just save the other HTML document.
Yeah,
right?
yeah. So you complete the cells. Some of them require you to add some coding. Right? Most of the cell may be already done for you, maybe 9%. There will be 10% of the cell that need you to complete some code. And then in order to run through, and then you save things to HTML, right? So I know that some students cannot have some bug, some error, right? So if that happens, just upload the IPy notebook file, okay? Because if you cannot convert to it, otherwise you convert to HTML, right? So this minimizes the TA's workload, okay? Yeah.
Okay,
otherwise,
thank you.
Yeah, you're welcome. Otherwise, TA has to put into the Jupyter server and then read your file. Okay.
Excuse me?
Yes? Yeah.
I have a question about the first file in the assignment 2. At the last, there's an exercise we need to separate, change the X and Y index to separate find the best combination to separate.
You are talking about the first assignment?
No, the second assignment.
Yeah, if you want, you can share a screen, maybe it will be clearer. Let me make it close. Yeah, if you want, you can share a screen, then we can take a look.
Yeah,
okay.
And right here, we need to change the X and Y. So what should we do here? I don't understand.
Yeah, can you go to the
could I make X, Y as the same numbers? I got the different types of separately looks well, but I don't know if it. What do you want?
Yeah, I don't remember the. Can you go to the question that we are asking you?
It's right here.
I believe so. I don't remember the details, but I think the answer right now you have is unlikely to be correct. Let me see. X index Y.
Code. The next one. I mean, just this code. I thought you just wanna change the X index and Y index. Change here. So if I change it to the other index, you can. Oh, I'm sorry. I need to rerun everything. So you can see it's very messed up. I don't know if it's gonna be satisfying.
I think because I think I run into a similar, not issue per se, but basically the index, I think you want us to kind of like change the index and see out the best way to kind of like separate the data. But apparently the index value that is currently on it is separated better than any other index value for me.
So for the question, you just want to find the combination of two parameters, separate the three classes, right? So
yeah. Okay.
you can see right here is a little bit messed up. What do you mean by separating?
Separating because
Actually, this one goes from 4-dimension to 2-dimension, right? So the X value could be 0, 1, 2, 3, Y value 0, 1, 2, 3. You take a combination of two values.
Yeah.
Let's say, X is equal 0, Y is equal 0. Just try it out, how the points are separated, clustered correctly. Then you change the value, X is equal 0, Y is equal 1, have a look at it. Then, change the value. Take the combination of X and Y. Then if you can cluster that points, like group them, that's a best one. Pick the best one combination.
Yeah, exactly. I think this one looks clustered, so I think it should be fine. But you can try different combinations. I mean,
what I'm saying though is the combination that you have on it. I think the combination that comes with the question was 1 and 2, and 1 and 2 seems to separate the data better than any other combination that you put there.
Oh, okay.
So my question is, if I leave it at 1 and 2, is that okay, or must I have to change the combination?
I think you can leave one that is best, but you can say how many you tried, right? So 1, 2, 0, 2, 0, 1, etc. Basically, I don't think they should be the same. Okay, so like both are 3. I don't think that's right. Okay, so basically you have a combination of 2 different values. Okay.
But Professor, how do we define the maximal separation? So here, though the data is well separated, but it's, we are talking about the classes, right? So here the data is visible in a scattered way, but in the previous plot, I don't know who is sharing the screen. Can you please show the previous indexes that you have put, petal width and petal length? I've also tried the same thing. I also felt it's right.
Yeah, basically, I think this is also fine. I mean, so it's if you just visually see that they are well separated, we will all content is correct. So we will not be so strict. If you have something that is totally like mixed, let's say the blue and the yellow points are mixed, then that's not right. Yeah, you can use your informed guess. Otherwise, you can define a metric, but we are not requiring this. There are metrics for clustering for sure. Yeah.
Yeah, I guess this only the last index, the last feature. I mean, if you put it all 3 here, is that's the only one totally separated.
But
no, that won't work.
Yeah, I know it doesn't make sense. I know.
Yeah, it doesn't make sense essentially. Yeah, so you need to have X and Y different. Okay.
Yeah.
Yeah, X, Y.
This one actually, Professor, I just wanted to ask this. Like we have 2 graphs, the previous one and this one. So I somehow believe that this is more informative because all the clustered, all the data, if I call them clusters, all these classes are, though they are not completely separated, but they are to the corner. So at least I can understand that, okay, petal length is between 0 and 0.8-ish. And I can clearly see the differentiation. How it is moving from. I can see the correlation between the data at least.
Yeah, I also say that, I also think this is better. Basically, you can see they are also clustered together, right? So if you look,
exactly, it's clustered together. Also, the varying values is also clearly visible.
Yeah, this is much smaller. If you look at the previous example, went down.
But what I'm saying though, this value, the index in these that he put in is 1 and 2. That's the original index that comes with the question.
Oh, if you think that's the best, then you just say that's the best. Okay.
Oh, okay.
Also,
yeah.
Also, Professor, I have a I have another question regarding the assignment. So there are multiple exercises and questions in the assignment. So do you want us to write in the same files and submit as HTMLs? Then it will be like 5 to 6 files, or do we want us to create a separate IPYNB file and
No.
answer each and every question?
You just work on, let's say this is a file 1, right? You just complete it and save to HTML file, save it to HTML, right? So
Okay.
yeah, so otherwise
Okay,
it's
then
too much
we
workload.
have to
You need to merge them, right? So yeah, file download as HTML. Yeah, so sometimes there will be errors. If that happens, then you have to upload the PY file. Okay, this file. Okay, original file.
Yeah, so we have to submit each and every file as HTML after answering the questions.
Yeah, if you can save to HTML,
Got it.
you save to HTML. If not, you tell the TA what's happening. Maybe that I know that some student have the NB convert error, and then and if that is really happening, then you can use IPy.
I'm sorry, Professor. I think I've not made myself clear. So, I mean, I was able to generate the HTML, but my question is, do I have to separate all the questions and create another file and answer them, then generate the HTML, or can I just answer in the same file and generate the HTML and submit it?
The latter is true. Okay, just complete it and file.
Okay, got it.
Yeah.
Professor, I've got a question too.
Okay.
On the assignment 3.2, not 3.2, but the 3.2 IPYNB. Can I share my screen if you don't mind?
Yeah. Thank you, Professor.
You're welcome. Who was talking? Who want to share the screen? Okay.
Oh, it's me. It's Emmanuel.
Oh, okay. Yeah, I need to make a call this one. Oh, okay. Yeah. You can share your screen now.
Okay, thank you. Can you see my screen?
Yes.
Yeah, this question right here, try a few parameters for each model and check the F1 score.
Yeah.
Do we have to list the parameter that we tried, or can we just try it on our own and then put down the best parameter? How do you want it?
If you are confident that what you tried is best, you can just put it there. But if you want to show TA,
I noticed. Yeah. I noticed on question number 4. Even though I'm not a PhD student, but that's actually the I use the grid search to get the parameters. So even if I do that, not being a PhD student, is that okay?
Yeah, that's totally fine, right? So this is an advanced requirement. So if you do the grid search, that's even better. Yeah.
Okay. Yeah, I did a grid search, but I'm a graduate student and not a PhD. But I use the grid search to generate the best parameters.
Okay, yeah, you can do that. But keep in mind, the grid search metric may not be the F1 score, right? So for the F1, it may be a little different still. Okay, so the grid search may be using accuracy as a metric. You need to double check. It's okay.
Well, the grid search just helped me generate the best parameters in terms of the.
In terms of some metric, but you have.
In terms of some metric, like I use it for the gamma, kernel, and yeah, those two, and yeah, the C, the kernel,
the hyperparameter. They try
the hyperparameter.
Yeah, hyperparameter to find the one that maximizes particular metric, do something. It may not be F1 score. Do you understand what I mean?
But what I'm saying, when I use the grid search and then I use those parameters and then I find the accuracy score for that particular parameters that was generated.
Yeah, exactly. So they're using accuracy. They're not using F1 score. So this third question asks you for F1 score. Okay.
I'm sorry. I also wanted to ask about the grid search. Like even I am trying with the grid search, but can I use the grid search to find the hyperparameter, then use the hyperparameter to calculate the F1 score, like train multiple models with different hyperparameters?
Yeah, you can do that. You can use a grid search to try to find a good one, and then then search around it. This is fine, right? But finally, you should report F1 score. It's not the accuracy. Okay.
I'm sorry. So, did you say you're reporting the F1 score? It's not the accuracy.
Yeah. So because the question asks for F1 score, not for accuracy. Okay. F1 score and accuracy are different. Do you understand what I mean?
Yes.
Correct. I understand that. Yeah, bro. I'm saying relating to these question number 4. So if I do the grid search and generate the parameters and then run the accuracy score on that and print out the accuracy score, is that not correct way that you want it to be implemented?
Yeah, for 4, it's totally fine, but it's not 3. 3 will ask for F1 measure, F1 score, right? You cannot use this to answer 3.
Oh, okay, that's what you're saying. But okay, I see what you're saying.
You can do this, and then you compute the F1 score. And you cannot use accuracy here to say you complete 3, right? So you can use here, find a good parameter, and then say, hey, F1 score is that, okay? And then you try a few values around the best accuracy point, right? Then you see this is really the best, right? So this is fine, okay?
Not quite okay. I think I got myself a little bit confused. Yeah, so I'm using 4 to generate 3. I'm using grid search for 4 to get the values for 3.
Okay, yeah, so that may not be correct. For example, for F1 measure, we look at precision and recall, okay? Precision means if you find all positive samples, right? How you think they are positive, how many of them are actually positive, okay? Recall means if their ground truths are positive, how many are found by you, okay? Accuracy means if it's negative, whether you reckon it negative, if it's positive, you reckon it positive. So these are different metrics, okay? You find the best parameter for this metric. Let's say this maximize the accuracy. It doesn't maximize the F1 score. Do you understand what I mean?
Yes.
Yeah, so you cannot use 4 directly answer 3. You can use 4 to find a parameter with good accuracy, and then starting from there, you explore a little bit and then report that F1 score, okay?
So basically what you're saying that the parameters that maximizes the accuracy score do not necessarily maximize the F1 score.
Yeah, basically grid search CV. Let me search for it. Okay, so that is some metric, but I don't think it's a F1 metric. Okay. But you can use grid search for F1 metric. I think there's some.
Yeah, I just looked in the sklearn, Professor, and I think you can use F1 score. Yeah, I was about to say that. So I'm also providing a link where it's related to module evaluation.
Okay, yeah. So you can basically for grid search CV, you can specify which metric you want to optimize. Maybe you can say, I want to F1 metric, but you need to make sure you are using F1 metric because by default it could be just accuracy. Okay.
Yeah, agree.
Okay. Cool.
Yeah, you need to study the
Emmanuel. I'm sorry, Professor.
Yeah, you go ahead.
Emmanuel, can you scroll up to the decision trees and random forest in the same file? I have a question I wanted to ask since you're already sharing a little more. Yeah. More. Yeah, underneath, can you scroll a little bit down, maybe to the 6th one, IN6? Yeah. Okay, so here, Professor, I'm not able to get the interactive plots. One, I'm having that issue. The second one is I do not understand this thing. Like, notice that at each increase in depth, what do you mean by the depth, Professor? Like the split activity?
Yeah. Depths basically if you have a tree, maybe next steps you split this further, right? So each time you split, right? So you find the attribute is split into 2, right? So maybe can you scroll these steps a little bit and see what it shows? Yeah, you see basically the first is split on this attribute, right? So the second is split, this node is split on this attribute, right? Because there are still 2 classes, right? And if you go to 3, yeah, thank you. 3. Yeah, now these two nodes each split on this attribute, the first attribute of this value again. So you separate these two, red and yellow. So this is the depth. It's okay?
Yeah, I mean,
So to create a decision tree, for example, the first level.
I'm trying to understand the problems that we are facing, like the overfitting. As we keep increasing the depth, the problem of overfitting comes in. Is that what you're expecting, Professor?
I don't remember the details, but the overfitting is basically saying if you cut here, above is red, below is some other not red class, this may be good. But if you cut too detailed, right? So you see here there are some mixed value, right? So you cut too small, maybe these are the noise. Okay, so maybe this should really be red, but unfortunately, someone labeled them as yellow, right? So if you go too detailed here, you think maybe next time we have a new point here, which is also red, right? You will think it's yellow because you have this node which is totally yellow. It's okay?
Yeah.
Yeah. So
I think I now understood the problem. The interactive plots are not working in my system. I think I have to go back and check with that.
Yeah, this is software installation issue. You need to Google a little bit to see how to make the interactive. I think it may be Jupyter Notebook version. Okay, you need to. It's something. It's a tool by Jupyter Notebook. You need to look at how to make it. Yeah, it's software.
I'll check with that, Professor. Thank you so much.
Oh, you're welcome. Okay, any other questions? Yeah, if not, you can send email to me, right? So and also the TA hours, you can find the TA. If you cannot make it in the TA hours, you can make an appointment with them, and or with me, and just send an email. Thank you.